Although in restricted contexts one may find this symmetry, the observable universe itself does not show symmetry under time reversal, primarily due to the second law of thermodynamics. Hence time is said to be non-symmetric, or asymmetric. However, quantum non-invasive measurements are predicted to violate time symmetry, contrary to their classical counterparts, although it has not yet been experimentally confirmed. Invariance. Physicists also discuss the time reversal invariance of local and/or macroscopic descriptions of physical systems, independent of the invariance of the underlying microscopic physical laws. For example, Maxwell's equations with material absorption or Newtonian mechanics with friction are not time reversal invariant at the macroscopic level, where they are normally applied, even if they are invariant at the microscopic level. When one includes the atomic motions, the lost energy is translated into heat. A toy called the Teeter-Totter illustrates the two aspects of time reversal invariance. When set into motion atop the pedestal, the figure oscillates for a very long time. The toy is engineered to minimize friction and illustrate the reversibility of Newton's laws of motion. However, the mechanically stable state of the toy is when the figure falls down from the pedestal into one of arbitrarily many positions. This is an illustration of the law of increase of entropy through Boltzmann's identification of the logarithm of the number of states with the entropy. Macroscopic phenomena, the second law of thermodynamics. Our daily experience shows that T-symmetry does not hold for the behavior of bulk materials. Of these macroscopic laws, most notable is the second law of thermodynamics. Many other phenomena, such as the relative motion of bodies with friction, or viscous motion of fluids, reduce to this, because the underlying mechanism is the dissipation of usable energy, for example, kinetic energy, into heat. The question of whether this time asymmetric dissipation is really inevitable has been considered by many physicists, often in the context of Maxwell's demon. The name comes from a thought experiment described by James Clerk Maxwell, in which a microscopic demon guards a gate between two halves of a room. It only lets slow molecules into one half, only fast ones into the other. By eventually making one side of the room cooler than before and the other hotter, it seems to reduce the entropy of the room and reverse the arrow of time. Many analyses have been made of this. I'll show that when the entropy of room and demon are taken together, this total entropy does increase. Modern analyses of this problem have taken into account Claude E. Shannon's relation between entropy and information. Many interesting results in modern computing are closely related to this problem: reversible computing, quantum computing, and physical limits to computing are examples. These seemingly metaphysical questions are today, in these ways, slowly being converted to the stuff of the physical sciences. The current consensus hinges upon the Boltzmann-Shannon identification of the logarithm of phase space volume with the negative of Shannon information, and hence to entropy. In this notion, a fixed initial state of a macroscopic system corresponds to relatively low entropy, because the coordinates of the molecules of the body are constrained. As the system evolves in the presence of dissipation, the molecular coordinates can move into larger volumes of phase space, becoming more uncertain, and thus leading to increase in entropy. One can, however, equally well imagine a state of the universe in which the motions of all of the particles at one instant were the reverse, strictly, the CPT reverse. Such a state would then evolve in reverse, so presumably entropy would decrease, Loschmidt's paradox. Why is our state preferred over the other? One position is to say that the constant increase of entropy we observe happens only because of the initial state of our universe. Other possible states of the universe, for example, a universe at heat-death equilibrium, would actually result in no increase of entropy. In this view, the apparent asymmetry of our universe is a problem in cosmology. Why did the universe start with a low entropy? This view, if it remains viable in the light of future cosmological observation, would connect this problem to one of the big open questions beyond the reach of today's physics: the question of initial conditions of the universe. An object can cross through the event horizon of a black hole from the outside, and then fall rapidly to the central region, where our understanding of physics breaks down. Since within a black hole the forward light cone is directed towards the center, and the backward light cone is directed outward, it is not even possible to define time reversal in the usual manner. The only way anything can escape from a black hole is as Hawking radiation. The time reversal of a black hole would be a hypothetical object known as a white hole. From the outside they appear similar. While a black hole has a beginning and is inescapable, the white hole has an ending and cannot be entered. The forward light cones of a white hole are directed outward, and its backward light cones are directed towards the center. The event horizon of a black hole may be thought of as a surface moving outward at the local speed of light, and is just on the edge between escaping and falling back. The event horizon of a white hole is a surface moving inward at the local speed of light, and is just on the edge between being swept outward and succeeding in reaching the center. They are two different kinds of horizons. The horizon of a white hole is like the horizon of a black hole turned inside out. The modern view of black hole irreversibility is to relate it to the second law of thermodynamics, since black holes are viewed as thermodynamic objects. Indeed, according to the gauge-gravity duality conjecture, all microscopic processes in a black hole are reversible, and only the collective behavior is irreversible, as in any other macroscopic thermal system. Kinetic consequences, detailed balance and Onsager reciprocal relations. In physical and chemical kinetics, T-symmetry of the mechanical microscopic equations implies two important laws, the principle of detailed balance and the Onsager reciprocal relations. T-symmetry of the microscopic description together with its kinetic consequences are called microscopic reversibility. Since most systems are asymmetric under time reversal, it is interesting to ask whether there are phenomena that do have this symmetry. In classical mechanics, a velocity v reverses under the operation of d, but an acceleration does not. Therefore, one models dissipative phenomena through terms that are odd in v. However, delicate experiments in which known sources of dissipation are removed reveal that the laws of mechanics are time reversal invariant. Dissipation itself is originated in the second law of thermodynamics. The motion of a charged body in a magnetic field, B, involves the velocity through the Lorentz force term Vb, and might seem at first to be asymmetric under T. A closer look assures us that B also changes sign under time reversal. This happens because a magnetic field is produced by an electric current, J, which reverses sign under T. Thus, the motion of classical charged particles in electromagnetic fields is also time reversal invariant. Despite this, it is still useful to consider the time reversal non-invariance in a local sense when the external field is held fixed, as when the magneto-optic effect is analyzed. This allows one to analyze the conditions under which optical phenomena that locally break time reversal, such as Faraday oscillators and directional dichroism, can occur. The laws of gravity also seem to be time reversal invariant in classical mechanics. In physics, one separates the laws of motion, called kinematics, from the laws of force, called dynamics. Following the classical kinematics of Newton's laws of motion, the kinematics of quantum mechanics is built in such a way that it presupposes nothing about the time reversal symmetry of the dynamics. In other words, if the dynamics are invariant, then the kinematics will allow it to remain invariant. If the dynamics is not, then the kinematics will also show this. The structure of the quantum laws of motion are richer, and we examine these next. Time reversal in quantum mechanics. Two-dimensional representations of parity are given by a pair of quantum states that go into each other under parity. However, this representation can't always be reduced to linear combinations of states, each of which is either even or odd under parity. One says that all irreducible representations of parity are one-dimensional. Kramer's theorem states that time reversal need not have this property, because it is represented by an anti-unitary operator. This section contains a discussion of the three most important properties of time reversal in quantum mechanics, chiefly 1. That it must be represented as an anti-unitary operator. 2. That it protects non-degenerate quantum states from having an electric dipole moment. 3. that it has two-dimensional representations with the property T2 equals 1. The strangeness of this result is clear if one compares it with parity. If parity transforms a pair of quantum states into each other, then the sum and difference of these two basis states are states of good parity. Time reversal does not behave like this. It seems to violate the theorem that all abelian groups be represented by one-dimensionally reducible representations. The reason it does this is that it is represented by an anti-unitary operator. It thus opens the way to spinors in quantum mechanics. Anti-unitary representation of time reversal. Eugene Wigner showed that a symmetry operation S of a Hamiltonian is represented in quantum mechanics either by a unitary operator, S equals U, or an anti-unitary one, S equals UK, where U is unitary, and K denotes complex conjugation. These are the only operations that act on Hilbert space so as to preserve the length of the projection of any one state vector onto another state vector. Consider the parity operator. Acting on the position, it reverses the directions of space so that P1x P equals x. Similarly, it reverses the direction of momentum so that P1 equals P, where x and P are the position and momentum operators. This preserves the canonical commutator x, P equals I, whereas the reduced Planck constant, only if P is chosen to be unitary, Pip1 equals I. On the other hand, for time reversal, the time component of the momentum is the energy. If time reversal were implemented as a unitary operator, it would reverse the sign of the energy just as space reversal reverses the sign of the momentum. This is not possible because, unlike momentum, energy is always positive. Since energy in quantum mechanics is defined as the phase factor exp, i.e. that one gets when one moves forward in time, the way to reverse time, while preserving the sign of the energy is to reverse the sense of I so that the sense of phases is reversed. Similarly, any operation that reverses the sense of phase, which changes the sign of I, will turn positive energies into negative energies, unless it also changes the direction of time. So every anti-unitary symmetry in a theory with positive energy must reverse the direction of time. The only anti-unitary symmetry is time reversal, together with a unitary symmetry that does not reverse time. Given the time reversal operator T, it does nothing to the x operator, Txt1 equals x, but it reverses the direction of P, so that Tpt1 equals P. The canonical commutator is invariant only if T is chosen to be anti-unitary, i.e. Tt1 equals I. For a particle with spin j, one can use the representation where j is the y component of the spin, and use of Tjt1 equals j has been made. Electric dipole moments. This has an interesting consequence on the electric dipole moment, EDM, of any particle. EDM is defined through the shift in the energy of a state when it is put in an external electric field, E equals D, E, plus E, where D is called the EDM, and the induced dipole moment. One important property of an EDM is that the energy shift due to a changes sign, under a parity transformation. However, since D is a vector, its expectation value in a state vertical bar must be proportional to vertical bar j vertical bar. Thus, under time reversal, an invariant state must have vanishing EDM. In other words, a non-vanishing EDM signals both P and T-symmetry breaking. It is interesting to examine this argument further, since one feels that some molecules, such as water, must have EDM irrespective of whether T is a symmetry. This is correct if a quantum system has degenerate ground states that transform into each other under parity, then time reversal need not be broken to give EDM. Experimentally observed bounds on the electric dipole moment of the nucleon currently set stringent limits on the violation of time reversal symmetry in the strong interactions and their modern theory, quantum chromodynamics. Then, using the CPT invariance of a relativistic quantum field theory, this puts strong bounds on strong CP violation. Experimental bounds on the electron-electric dipole moment also place limits on theories of particle physics and their parameters. Kramer's theorem. Kramer's degeneracy theorem. 40, which is an anti-unitary Z2 symmetry generator. T2 equals UK equals U star equals U, Utah, 1 equals. Where is a diagonal matrix of phases? As a result, U equals Utah and Utah equals U, showing that U equals U. This means that the entries in are 1, as a result of which one may have either T2 equals 1. This is specific to the anti-unitarity of T for a unitary operator, such as the parity, any phase is allowed. Next, take a Hamiltonian invariant under T. Let vertical bar and T vertical bar be two quantum states of the same energy. Now, if T2 equals 1, then one finds that the states are orthogonal, a result called Kramer's theorem. This implies that if T2 equals 1, then there is a twofold degeneracy in the state. This result in non-relativistic quantum mechanics presages the spin statistics theorem of quantum field theory. Quantum states that give unitary representations of time reversal, i.e., have T2 equals 1, are characterized by a multiplicative quantum number, sometimes called the T-parity. Time reversal transformation for fermions in quantum field theories can be represented by an 8-component spinor, in which the above-mentioned T-parity can be a complex number with unit radius. The CPT invariance is not a theorem, but a better-to-have property in these class of theories. Time reversal of the known dynamical laws. Particle physics codified the basic laws of dynamics into the Standard Model. This is formulated as a quantum field theory that has CPT symmetry, i.e., the laws are invariant under simultaneous operation of time reversal, parity, and charge conjugation. However, time reversal itself is seen not to be a symmetry. This is usually called CP violation. There are two possible origins of this asymmetry, one through the mixing of different flavors of quarks in their weak decays, the second through a direct CP violation in strong interactions. The first is seen in experiments, the second is strongly constrained by the non-observation of the EDM of a neutron. It is important to stress that this time reversal violation is unrelated to the second law of thermodynamics, because due to the conservation of the CPT symmetry, the effect of time reversal is to rename particles as antiparticles and vice versa. Thus the second law of thermodynamics is thought to originate in the initial conditions in the universe. Time reversal of non-invasive measurements. Strong measurements, both classical and quantum, are certainly disturbing, causing asymmetry due to second law of thermodynamics. However, non-invasive measurements should not disturb the evolution, so they are expected to be time-symmetric. Surprisingly, it is true only in classical physics, but not quantum, even in a thermodynamically invariant equilibrium state. This type of asymmetry is independent of CPT symmetry, but has not yet been confirmed experimentally due to extreme conditions of the checking proposal.